All right. So, well, thank you for coming back for this session. So you're still on the theme of focusing on cyber insurance and risk and control and machine learning for insight in cybersecurity and situational awareness. We are now on track 6, cyber threat intelligence, OSINT, and cyber microbiomes. And we will have 3 talks followed by a 30-minute break and then a keynote again from Jason Nurse. So our first speaker for this track is going to be Aikaterini Kanta, and she will be talking about smarter password guessing techniques, leveraging contextual information in OSINT. So Aikaterini, sorry, the floor is yours.
Thank you very much. I don't have control of the slides. Yep.
You should be able to go, yes, on the arrows at the bottom. Yep, perfect.
Thank you. Hi, everyone. So this talk is about smarter password guessing techniques, leveraging contextual information and open source intelligence. And it's a collaboration between University College Dublin and the European Commission's Joint Research Centre. So open source intelligence, it's something that has been used even in World War II. It was called overt intelligence, and its main source was an press, and it was used to look at the image of public opinion. But nowadays, it has evolved. It includes online sources like social networks, whois domain records, traditional media like newspapers and television, academic publications, geospatial information, and any publicly available data like government reports. One of its advantages is its availability. It's accessed from anywhere at any time. And another advantage is the volume, because you can have access to very big amounts of data. But that's at the same time a disadvantage, because it's very difficult to sort through, and it's not very easy to evaluate the quality. Now there are various forms of open source intelligence, but we're just focusing on the ones you see. There is human intelligence, which is information that is collected by humans, and it is provided by human sources as well. There's social engineering, which is very similar to human, but it's focused on social interactions, and it can include physical attacks like dumpster diving, reverse social engineering, technical attacks, and most recently, social media attacks. Then there's also SOCMIN, which is social media intelligence, which is applied to groups or individuals for establishing behavioral patterns and can be used to predict and identify online threats. Finally, there's crowdsourcing, which is collecting investigative leads by public to aid an investigation. One of the advantages is that it's very low cost and it's very fast, and there is a large and varied crowd of people that do it. And it's also flexible. It's not hindered by time zones or bureaucracy. Sorry. So open source intelligence for law enforcement. It was used even before the digital era, where law enforcement collected the available information through traditional sources like victim accounts and witnesses accounts and physical evidence at the scene of the crime. But nowadays, it can be enriched by online sources thanks to open source intelligence. This means that the monetary and manpower costs are minimal, and this makes it very useful for law enforcement. It could include social network analysis, where law enforcers identify relations between different entities of a criminal network. They're collecting evidence online, analyzing the interactions and online activities of criminals, and looking at the patterns and the ties of the involved actors. There's also crowdsourcing, an example of which is Europol's Trace an Object campaign, which basically asks individuals to examine objects in the background of images of sexually explicit material and to identify the origin of the object. And another example is Traffic Cam, that asks users to upload images of hotels they've stayed at in order to create a database that can then be used by law enforcement for the same purpose. Here is a list of some tools, open source intelligence tools, that can be used, the websites, and then the notable usage for each tool. So for password guessing techniques, there is the ones that we use traditionally, like brute force and dictionary attacks. And more recently, we have techniques that are based on Markov chains, probabilistic context-free grammars, long short-term memory, which is an artificial neural network, and generative adversarial networks. So what we want to look at is the context in passwords. The average number of passwords one user has to remember varies between 27, according to one study, to 191, according to another study. That means that users tend to select passwords that are easy to remember, but ultimately very weak. Or they tend to reuse a potentially complex password with or without making some slight modifications to it. In the first 9 months of 2019 alone, almost 8 billion records were leaked in various data breaches. Another study has shown that users generally have a very biased understanding of password security. For example, they tend to overestimate the security increase by adding numbers at the end of a password, and they tend to underestimate the predictability of using keyboard walks or common phrases in their passwords. Some of the categories that play an important role in passwords, as you can see, are demographics, personal information, and user interests. Indeed, one study has shown that professionals tend to use passwords with an average length of 8 to 11, while students use passwords that are shorter. And also another study has shown that for Chinese users, more than 50% of them are using passwords that are only numbers, with 12% of these passwords being birthdays or phone numbers, and 11.5% being usernames and emails. Users tend to use familiar models when they create a password. For example, they use the expression of feelings, emotions, names, dates, places, things that are more easy to remember. And ultimately, the culture and the country of origin of the person plays a role. The same is true for the purpose of the website that the password is for. Because, for example, for a website about banking, users tend to choose stronger passwords than for a forum that is of a generic nature. So this brings us to leveraging the context of passwords, because many times during the course of the investigation, law enforcement forces are faced with a password protected device, and they have to access it to advance their investigation or to resolve their investigation. So the purpose of our research is to aid law enforcement when traditional password protecting methods have not been fruitful, or they're too time consuming and there are time restraints. And the way we want to go about doing this is by focusing on what we know about the suspect, meaning the digital life of the suspect. That means that we're focusing on local device information, which is information that is gathered from the analysis of a seized device at the physical scene, which could include the browsing history on a computer or laptop, or, for example, a poster in someone's room that shows that they like a certain type of music. There's also their social media presence, where criminals use social media the same way as average users do. And you can find their connections and their interests. And law enforcement can also use the information from social media to create a more detailed timeline of the whereabouts. And finally, previous passwords, because they can showcase the patterns a person uses when they create a password and the type of modifications they use when they're using similar passwords. And also how many of these passwords they use again and again on different websites. So all of this information that we know about a suspect can help us build what we're calling a personalized dictionary that is focused on one individual and it's tailored to them. So what we know about password usage in general, but also for the individual, can help us choose the mangling rules, which are, as you can see, different type of modifications a user can make on their password, like using leet speak, for example, replacing O with a 0 on the password, or appending filler words. So instead of my password, instead of same password, they're using my password, or adding numbers at the end of the password. There are many different rules, and previous passwords can show us the tendency users have towards specific type of rules. And therefore, with the personalized dictionary and the mangling rules, we can create a smarter dictionary list that is focused on that one specific individual. This is the idea. And now I will speak a little bit about our progress so far. So what we've done is we have used the Have I Been Pwned list, which is the largest available dataset of leaked passwords that contains 3.9 billion real-world accounts. That means, well, 3.9 billion real-world accounts, meaning 500 million unique passwords, because a lot of these accounts use the same passwords. And what we've done is a statistical analysis on the Have I Been Pwned dataset. We've looked at length, password structure, and password strength. And we've also done a fragment analysis, which I will talk more about later, and a classification with WordNet. So our Have I Been Pwned analysis. On the first table, you can see the top 25 passwords in Have I Been Pwned. Those are the passwords and the percentages of total accounts. You can see that a lot of these passwords are familiar to you because they feature heavily on a lot of worst password lists. And a lot of them are very popular because they're sequences of numbers, they're very common words, or they're keyboard walks, like QWERTY. Then you can see that we've done what we're calling a pattern analysis, the type of masks in Have I Been Pwned. Typically, there are 4 classes of characters in passwords. There's lowercase characters, uppercase, numbers, and special characters. And this graph shows the most popular combinations of these types. These combinations are what we're calling masks. As you can see, these are the 15 most common ones, and the most common one by far is string digit, which means that there is a string which could be lowercase or uppercase, followed by 1 or more numbers. This makes sense to us because users typically pick an alphanumerical string. It could be a common word or a name, and then they add numbers to the end, usually to fulfill the length and character set requirements by the password policy. The next most common categories are string, digit, and digit string. And these 4, the top 4, represent over 75% of passwords. So you can see that there are some categories that are most common even in such a big data set. Next, we have the length distribution in Havebin-Pont. As you can see, 8 characters is the most popular category with about 30% of passwords. There is a probable explanation for this, and that is that most password policies require 8 characters at least. And the second most frequent category is 10, which corresponds to 17% of passwords. Overall, the lengths we found were from 1 to 449, but 84% of the passwords were between 6 and 12 characters long. And finally, we have done a strength analysis, and for that we have used ZXCVBN, which is a password strength metric. It was originally deployed in the Dropbox service. And this metric attributes an integer score between 0 and 4 to each password according to strength. As you can see, almost 50% of the passwords are in category 2, and the most secure passwords, which are in category 4, are about 12%. So we've also done what we're calling a fragment analysis. As you saw in the masks in the previous slide, a lot of passwords contain more than one type of character. So what we've done is that we've cut passwords into fragments. As you can see, we have a total of 1.5 billion fragments. And since the data set is 500 million passwords, we see that a lot of the passwords do indeed contain fragments. So the breakdown of the fragments can be shown here. These are the 10 most popular fragments per category. As you can see, A and I are at the top for letter fragments because they're classified as an article and as a pronoun. And then we also have fragments that, again, could be encountered in the top worst passwords like QWERTY, love, my, ABC. We also have keyboard walks, we have single digits, and we have sequences of numbers in the number category. And then for special characters, we have mostly single characters, which to us makes sense because people tend to avoid using characters that they have to type 2 keys to insert. As you can also see, there is an order of magnitude of difference between special characters and letter and number characters, which shows again that letters and numbers are a lot more popular. Finally, I will give you some details about some of the fragments we found in the top 500, which I couldn't include in the slide, but we encountered a lot of 4-digit numbers that were between 1,900 and 2020, with 2010 being encountered in position 56, and overall 37 4-digit numbers between 1,970 and 2010 appear in the top 200. This leads us to believe that users often choose memorable patterns for the number portion of the passwords. They choose things like year of birth or other important dates. Also, for special-based fragments, there's a lot of them that are just repetitions of the same character. So a lot of exclamation points, one after the other. But we also saw some more meaningful structures that represent, for example, emoji characters. We have as well the most common fragments per category. We've used WordNet to classify the fragments according to categories. And as you can see, the 3 most popular ones have numbers in them, which are single numbers, common numbers like 1, 2, 3, 4, 5, or years. This can be explained in part because of the password policies that are in place, because usually they require you to have one to have letters and numbers, which means that a lot of users place some numbers at the end of the password. And it can also be explained by the fact that numbers are very popular in Asian countries, because, for example, they're a lot more easily entered digitally than ideograms. Finally, you can also see that in the top 25 fragment categories, we find a lot of semantically rich categories, such as cities, emotions, sports, family, things that reinforce the idea that the surrounding context of a person can influence the choice of the password. So our conclusion is that when possible, common approaches should be always contacted first, because according to our strength analysis, approximately 80% of the passwords in Have-I-Been-Pwned belonging mostly to class 3 and below can be recovered with traditional methods. And then if those approaches fail, then we have to look at how we can use contextual information to continue the recovery process. So part of our future work, because we've seen that there's a lot more to be done with the number fragments, we want to look at the habits of users regarding numbers, and how we can better classify the number fragments. We also want to look at different language models for letter fragment classification. And finally, we want to focus on smaller datasets that stem from specific communities, because we believe that, for example, if we have a dataset that is about video games, we're more likely to encounter words with contextual, with meaning that is close to video games, than if, for example, we were looking at a website about the dataset about cooking. So this was my talk. Thank you very much. If you have any questions, I would be more than happy to answer.
So thank you, Aikaterini. All right, so I've got one question. You mentioned that the top passwords are 1 to 3 on one of your slides, and you had a list of like the 25 more top passwords. I was wondering if you had looked at the services those were used with, because, for example, would the password not depend on the service? If it's a service that people use sporadically, or they know that they are not going to use it anymore in the future, maybe they actually use like one of those weak passwords. Would that affect the 20 most top passwords?
We actually believe that it would. The thing about the dataset we used, Have-I-Been-Pwned, is that it's assembled by a lot of smaller datasets, but we don't know the origin of them. So we cannot make assumptions about where the password is originating from. But we did notice that in class 4 passwords, which were considered the most safe, we saw passwords from usually 11 digits and above. And what we want to do with focusing on smaller data sets is what you said, that maybe we can see that in specific forums, the strength of the password changes according to what the website is for.
Yes, I think that would make sense depending on like the type of website and the type of user and how many active users you get. And like if the user intend to retain those users, you might have like stronger passwords, whereas like a website that might not be for retaining users or no intention to retain users, then might actually have like a weaker password. This would be interesting. So if you looked at like the different communities at some point, like you mentioned communities, is this like something that you believe will affect the strength of password or the type of password strongly?
Because we found context in Have-I-Been-Pwned, which is very diverse, as I said. We believe that more focused communities would definitely have more passwords that are targeted towards these communities. But we do want to test it and see if it's a correct assumption.
And then another question is, do you have a plan to strengthen those passwords over time, or like to help people strengthen their password? Because at the moment you've been doing an analysis of passwords, but what's the route for people to actually learn that strong passwords are important, and like when should we start educating people about strong passwords?
To be honest, we don't have a plan about that because we're mainly looking at passwords from leaked datasets and not how we can educate people on picking safer passwords. But I believe that the results we will get from this study will provide insights into how we can make password selection more safe.
Perfect. So we have no more questions. Well, thank you, Aikaterini, for this great presentation. And we are now going to continue with